Hi friends, welcome to my channel. Let's have a look at problem 2359. Find closest node to given two nodes. This is today's daily challenge problem. In this video, we're going to share a treatment based on breadth-first search. First, I'll read through the problem statement to digest the task, and then we do the analysis, and finally we share the code. First, the problem statement. We are given a directed graph of n nodes numbered from 0 to n-1, where each node has at most one outgoing edge. The graph is represented with a given zero-indexed array called edges of size m, indicating that there is a direct edge from node I to node edges I. If there is no outgoing edge from I, then edges I would be -1. So we are also given two integers, node 1 and node 2. So the task is to return the index of the node that can be reached from both node 1 and node 2, such that the maximum between the distance from node 1 to that node and from node 2 to that node is minimized. If there are multiple answers, return the node with the smallest index, and if no possible answer exists, return -1. So here is a note which says that the edges may contain circles. So here are two examples. So we are going to analyze example 1 in some detail and an example. So here the output is 2. And in example 2, so the output is 2. So the node corresponding is actually 2, right? Here is an explanation. For example, the distance from node 0 to node 2 is 2, and the distance from node 2 to itself is 0. So this is the maximal of this 2 is 2. Here it's also the minimal. So before we do the analysis, let's also look at the constraints. First, n is the length of the edges list, and it's bounded below by 2 and bounded above by 10 to the power 5. And each of the edges is in between 0 and less than n. So here -1 is special because if there's no outgoing edges for that node, then it will be a -1. So edges I does not equal to I. So this is the additional assumption, right? So secondly, node 1 and node 2 are in between 0. This is inclusive and less than n, right? So with that said, we are ready to look at the analysis. First, this problem relates to the shortest distance. Therefore, we should think of breadth-first search. And also, we want to check from which node can be reached from a given source, either node 1 or node 2. So in other words, we need to consider the connected component with a source, right? So this is the overall problem and information. So here for the coding, actually we can, for each node, we can find the corresponding connected component, and we want to add additional information, and that is the nodes in that component and the distance of those nodes with the source. And then we want to check the common keys in the two connected components, and then select the one satisfies the problem requirement or return requirement. So here let me comment again. So rather than just recording the nodes in a component, we also associate the node with the distances to the source. So therefore, for connected component, we now return a dictionary abstract data type with more information than the set abstract data type. So here is a walkthrough for example 1. For example, so we can reach 0, 2, and 3. So the distance is 0, 1, 2 respectively. And from node 2, that is 1, we can reach 1, 2, 3. So the distances are 0, 1, 2. So 2 and 3 are the common keys. And because the maximal corresponding to node 2 is less than the maximal corresponding to node 3, so we're going to return 2 for this example. So similarly, you can analyze example 2. So this is this analysis also gives us the overall idea. So first, we are going to build the graph according to the given edges. So actually, this is just for convenience of doing breadth first search. So you can actually keep the edges format. So this is the one thing. Next, we are going to write a breadth first search hyperfunction to locate the connected components, also with the distance information. And finally, we check the keys and prepare the return. So with that said, let's look at the coding. First, build this graph. So for this, I'm going to use collections default dictionary. So I'm going to use node and their neighbors. So for storing their neighbors, I'm going to use the container site, right? And then we're going to iterate over the edges. So for start and end in enumerate edges. So if end is not -1, in other words, there is indeed an edge from start to end. So we're going to do graph start at the end, right? So this actually finishes building the graph. And next, so the breadth first search hyperfunction. So this is actually a very standard task. So first, let me define this as BFS. So we're going to accept a source, and then we're going to return the dictionary containing the nodes in the corresponding connected components and their distances, shortest distances to the source. So for this, I'm going to initialize a dictionary called result, and then we're going to use a queue. So collections, so we're going to use deck for queue. So originally we have a source and the distance to itself is 0, right? And then we're going to do this while queue. So we have the node and distance, that is queue pop left, right? So here we are using this as a queue. And then we're going to add this information, result node equals D, to the dictionary. And then we check the neighbors in a cascading way. So for node, for neighbor in graph node, then if neighbor not in result, and then we're going to append the corresponding information. That is, the neighbor and the distance will be D plus 1, right? So this way, after we exit this while loop, so we find the corresponding components or the nodes we can be reached from the source. Then we return this result variable. So this is the second step. Next, we are going to check the keys and prepare the return. So for this, and let's first call this breadth first search function to get the connect components. That is node 1 and BFS node 2. And then for convenience, I'm going to use a variable called distance and result to monitor the distances and the maximal distances and the node. So I'm going to use float infinity and float infinity. This is just for comparison and due to the problem requirement. And then what we are going to do is to iterate that for node in C1. So if node also in C2, and then we are going to get the current maximum, right? So C1 node and C2 node, right? So if the current maximal distance is less than the dist, and then we are going to update the dist to be temp and the result to be the current node. So this is one case. Another case is the temp happen to equal to dist. And in this case, we want to find the smaller index, right? So we are going to set if node is less than result. So that also explains why we initialize this as a float infinity at the very beginning. So we're going to set result to be node. And then we do the return. So we return result if result is not float infinity, right? In other words, there is a such a node. Otherwise, So we're going to return -1 according to the problem requirement. So with that done, actually this forms a solution format to this problem. So the overall structure is like the following 3 steps. First, we build this graph for convenience of doing breadth first search, and then we write the breadth first search function to get the connected components with distance information. And the third step is check the keys and do the return. So with that said, let's first do a check. Yeah, this passes the first example. Now let's look at the generic case. Yeah, it passes all the test cases. Let me submit again. Yeah. Yeah, with that said, I guess that's about it for this specific problem. You are welcome to check out other videos in my channel and share the channel with your friend if you find something new in this channel. Thank you.